Hello, everybody. Looks like SONET and OTN is already scaring folks away. Apologize for that. My name is Christian. I work for Cisco, and some of you might think OTN, SONET, is he going to waste my time? I hope I will not. What I'm going to talk about is how to deliver private line services over MPLS. And I think we have talked about that, or the industry has talked about that for many years, so I'm not going to repeat that. But I think a few things have changed, and I want to share some trends, and maybe make you start think, and maybe there is some discussion coming out of this in the industry. So when we talk about private line services, you know, if we go back a couple of decades, it was mostly about DS1 circuits in between routers using serial interfaces, right? Good old days. Then Ethernet became, let's say, a more and more adopted and accepted technology in the wide area network. But I would say, particularly in the North American market, fiber wasn't always there where you needed it. So Ethernet over SONET, basically running Ethernet over a PDH or SONET infrastructure, became a predominant use case. And as traffic grew, of course, now we talk about 10 gig, 100 gig, basically big fat point-to-point pipes that either get delivered by a carrier, right, or get bought by an operator that wants to build his network infrastructure, right? And commonly they are used today or deployed today using some kind of DWDM setup, maybe mux bonders. Sometimes they are, back-to-back patched or whatever, or OTN as a switching technology is being adopted. So I think one point here is that all these private line services, I would say, have two things. One, they are quite costly, and I'm not running an operator, so I can't really speak for that, but I think that is pretty much true. But also it is quite costly or cumbersome for providers to even provide them, right? Building a 100 gig pipe from A to Z anywhere in the US, is probably not that easy, and it's going to take a while until you get one, right? So this is not very agile. So what have those private line services in common? The first and the last one, I would say, is important for those of you that provide those services, right? You want to provide them as cheap as possible, and you want to have a simple operation for running those, right? Both of them drive your cost and basically drive your profit. On the flip side, the folks that actually need those pipes, they are concerned about how that pipe is going to behave, right? It needs to be low latency, guaranteed bandwidth, it needs to be highly available. You want to have sophisticated OEM and things like that. Let's touch point on the first one, which is cost. And I think this is actually good that we have had the session before. We were just talking about 1IU pizza boxes, 10 terabit, 4 terabit, right? Even more coming on. The capacity that MPUs and ASICs are today delivering for packet forwarding is just massive and amazing. It's actually, I would say, mind-boggling. I remember when I was designing routers and we were trying to get a 10 gig card out of the door with some QoS. It was a pain, right? Now you just put an MPU on a card, a bunch of cards together, and you have a box, right? It's way different. Now, what do we see on the TDM side? We already see that OTN is lagging behind, OTN being the successor of SONET, right? So this is, I think, a very important point to remember. If you tend to believe or want to provide those high-capacity services using OTN switching, you should bear in mind that the cost per bit of OTN is not going to be that good, and it will not be able to pick up with what packet is allowing you. Another thing is, if you want to build an OTN switch that's big now, you typically do what is shown in this picture, right? Investment in TDM silicon has really stopped. So you're not going to use a classical TDM crossbar. What you're actually going to do, you're going to throw in some kind of cell-based fabric, right? And one predominant example is the DNX product line from Broadcom, aka Jericho or Out, whatever you want to call it. And around that, you put OTN framers. The OIF has defined a protocol or an implementation how you can take OTN frames and basically hand them over to a cell-based fabric. And then on the other side, the OTN framer takes the cell stream and then basically regenerates the OTN frames, right? So that's how you build an OTN switch that scales to terabits of capacity. The interesting part is, most of you, I guess, already know, this thing in the middle is really more or less a router now, right? It's not only a fabric interface. It does some decent packet forwarding, and actually it's getting better and better. So if you take the OTN framer away, you remove 2 out of 3 chips per line card. And by the way, if you're not using interlock in between the framer and the Jericho chip, you can actually put 2 more 100 gig interfaces on the Jericho. So you get a 600 gig per slot system rather than a 400 gig per slot system. More capacity means lower cost per bit. And then, if you want to go wild, right, if we're going to take away the 450 millimeter depth or the 300 millimeter depth, right, if we want to build the boxes different, no longer the front to back where we bend the air kind of design, but we take the classical data center approach here, we can stick 6 of those MPUs onto a card, gives me roughly 3.6 terabits, times 16 slots, you can take them off. This is a lot of terabits per rack, per half rack. Again, you're driving down the cost. And as those MPUs grow, you're going to get bigger number and bigger numbers. So let's just assume we have decided we want to run this over MPLS, right? How are we going to do this, right? I mean, we all know that IP MPLS is connectionless, right? So we need to somehow get a representation of that connection, right? Thanks to Luca Martina and a bunch of other people, many years ago, they defined the Pseudowire, right? The Pseudowire is giving us a representation of a point-to-point connection between 2 attachment circuits. It has been defined for any type of attachment circuit, DS1, frame relay, ATM, and Ethernet. I would say, while many years ago, the whole topic about migrating ATM and frame was a big one, I don't think that ever really picked up. Predominantly, you use Pseudowires for Ethernet transport, right? But it's still widely defined for everything. A Pseudowire, though, doesn't really have a notion of bandwidth and path in its purest definition, right? So it's just a point-to-point connection. It's an association between 2 endpoints, right? So if we want to have some notion of path and bandwidth, we're going to use an MPLS LSP in between, right? And that MPLS LSP is giving us 2 things. For example, it lets us deal with bandwidth, and it lets us deal with deciding how the path needs to go through the network. Is this real, and how people are doing this? And actually, Verizon, you might have seen this, is publicly talking about this. A couple of years back, they started adopting this technology, not for Ethernet, but they're also using it for Ethernet. But per se, the new thing is they're actually doubling down on modernizing their SONET infrastructure and using circuit emulation and MPLS Pseudowires. They're today running actively circuit emulation in the X's, which is shown on the top. That's where they're actually doing an interesting trick. In areas where they don't have fiber or resources, where they're actually relying on third-party carriers to provide DS1 circuits, they're migrating to a common Ethernet service from a third party, and they're consolidating multiple DS1s as well as Ethernet services using Pseudowire and MPLS technology. And as we speak, they're going down the middle and the bottom picture, where they actually more widely deploy MPLS in the metro and trying to modernize all the TDM infrastructure. And all of you probably can imagine this is going to be a huge undertaking, because essentially what you're trying to do, you're trying to migrate a museum. I mean, I have been myself in a central office at Verizon, and I couldn't believe what I have seen, right? I mean, it's really mind-boggling. And over the years, a lot of equipment has been collected, and they basically need to migrate that. Some of it, maybe they can just turn off, but some of it they can't. They need to migrate the services. Now, once you go down that path, right, depending on what you want to do, you might actually care a little bit about how you run your network, right? Some of you or some providers may say, well, if I migrate just a bunch of DS1s and I have a 400 gig backbone, I don't care, right? But some might say, well, my infrastructure may be actually just as big as I can migrate my services. So you might want to be a little bit more stringent in terms of how you run your network and how you route your LSPs. Again, this is not rocket science, right? All of you guys know this, right? The left picture is classical traffic engineering, right? We compute our paths at the head end. We're going to run our setup, and we're going to map our pseudowires onto label switched paths. Of course, you can also do it in a more centralized fashion. I would say this is where segment routing and a lot of the PCE and PSEP and SDN-centric approaches are feeling at home. Whether you do it either the left or the right way, it doesn't really matter. The point is that you actually start dealing with LSPs and bandwidth management a bit more in tight. So I talked about we're mapping pseudowires onto LSPs. So let's spend a minute on that. Essentially, the first way to do that, in particular if you want to map point-to-point private lines, is some kind of a one-to-one pinning, where basically you say this pseudowire goes onto this LSP, this pseudowire goes onto this LSP, right? This actually has a nice side effect, because as you have a one-to-one relationship between your pseudowire and your LSP, you can also keep track of the bandwidth, right? So traffic engineering and path computation is making sure that I only put as many LSPs onto a particular link as I have bandwidth available on that link. And with this bandwidth management or pseudowire CAC, you can now also assign a bandwidth to a pseudowire and keep track of how many pseudowires you map onto the LSP. So now you get really this end-to-end bandwidth admission that you get from SONET and OTN, where essentially you're going to only assign time slots that you haven't assigned yet. The other approach is you're going to turn on the autopilot, right? What you're going to do is essentially you could run auto bandwidth on your LSPs, whether it's on box or off box in a controller. I mean, that depends on your choice. But essentially, you're gonna adjust your LSP bandwidth based on traffic measurements and continuously monitor how your network is loaded and reroute potentially LSPs as needed. While you do that, you normally would also then auto-route announce your LSPs, which means basically your LSPs become links in your topology or in your routing table. And then the pseudowire traffic is going to dynamically getting diverted or injected into LSPs based on which one is the best to reach the destination. Okay. The next service level agreement parameter that we want to look at is availability. Again, this is not something new, right? Traffic engineering is known to everybody. Fast reroute is, I guess, also known to everybody. We have a primary path. We have call admission controlled it across the network. And for each and every link or node that we want to protect, we're going to calculate some detour LSPs. Traffic engineering fast reroute uses this model where basically we're going to look at all the interfaces we want to protect. We try to find one of those green detours, and we're going to try to get back to the previous or primary path as soon as possible, right? Depending on whether you look for link or node protection, you might go a little further, but essentially always try to get back to your original path. So when a failure happens, essentially we can do a local detection and a quick reaction. And traffic is going to go a short little detour. This is kind of like when something happens on the highway and you're going to get diverted to some other roads. Important, while we have done some quick local reaction, we also do global convergence. So after some time, we're going to look for a new working path and for a new path for the LSP, and we're going to route, for example, in my topology, the traffic on the bottom side. If you would adopt segment routing, something very similar is happening in your network. Either just by plain segment routing or maybe using a segment routing policy, again, our traffic may, in normal situation, run on the top blue path. Also, we're going to look at all the different nodes and all the interfaces and nodes we want to protect, and we're going to pre-compute and pre-program what we now call a loop-free alternate. This is very similar to the FRR model, but there's a small little difference here. We no longer try to get back as soon as possible to the actual path of the LSP, but rather we're going to look from a point of repair perspective, what is the most optimum and suitable path towards the destination. And this is giving us more along the line what we call the post-convergence path. Because if I click the clicker here, this is the immediate reaction, but once the network converges, this blue path is pretty much the same as this green path, and depending on the topology, they might be exactly the same. So what does this mean, or what's the important point that I want to point out here is, we need to deal with two situations, right? One is the immediate reaction. You're going to have some network utilization. And the other one is the situation of the network when the network has converged for the failure. And in order to deal with that, you need to implement some kind of network planning and optimization, right? I guess, again, this may not be news to you. I mean, if you run a network, you always want to plan it and optimize it. But in the context of talking about a more traditional SONET or OTN type of network operation, I think this is an important point. It's not about set and forget. You're not just allocating time slots and then you don't do anything. You really more use a dynamic network that you constantly need to monitor, but for the benefit that you have much more capacity at a lower price. Now, the third option, if you really want to be very TDM-centric in your behavior, is to adopt a path protection model. And that actually has one benefit. You don't have to really deal with this immediate reaction and post-convergence, right? All you have is a working path that you, again, call it mission control and setup, and a protect path. And the protect path is shown in green on the bottom. Adding bidirectional and co-routing aspects to it, which have been defined a couple of years ago, you can actually also ensure that the forward direction and the reverse direction is going along the exactly same path. And that has the benefit that you have equal or very close to the same latency in both directions. In this model, we essentially need to kind of get an idea of whether the working in the protect path at the head and both endpoints is still available. And in order to do that, we need to use some end-to-end liveliness. And in case of MPLS, BFD is used here. So we are exchanging BFD keep alives on both the working protect, and that allows us to find a failure anywhere along the path, right? The local protection schemes, FRR and loop-free alternate, are relying on local failure detection, so they don't need to find out that there is some kind of remote failure. So once we detect the working path has a problem, we now at the head end can decide not to send traffic on the working path, but on the protect path. The important point here, why can you stop dealing with immediate reaction and post-convergence situation, is both the working and protect path have been pre-signaled and bandwidth has been allocated. So whenever you switch over, you know already in advance that you're going to have enough bandwidth there. That makes running the network in a very TDM-centric way much easier. But there actually have been a couple of wrinkles that we uncovered. And they are coming from, let's say, the roots of IP MPLS being very dynamic and being optimized to adapt to changes in the network. If the working path changes, we're going to switch to the protect. But what RSVPT dynamically does or automatically does, it is looking for a way around the failure. And if there is one, it will reestablish the primary path. And this is the blue zigzag path that I'm showing here. And also at the same time, the head end will start switching back from the protect to the working. Now, a lot of folks would say, well, I don't care, why not? But in the strictest TDM-centric way, this is something that classical SONET networks and OTN networks don't do. So if you want to emulate that behavior as close as possible, you need to stop doing that. There was actually a very easy way to do that, is by just implementing something that we from Cisco call sticky path, for lack of a better word. I guess the more clever name could have been persistent. Essentially, we want to make sure that my previously established working path stays persistent. Essentially, we're going to keep it in our memory, and whenever we try to establish it, we're always going to try that old path. This is something that classic RSVPT doesn't do, but with this small knob here, we can now make the behavior look very much like SONET and OTN. Another thing that IP MPLS networks don't do, but SONET and OTN networks, something that IP MPLS networks do, but SONET and OTN networks don't do, is revert automatically back. And I think this difference probably comes from the fact that the TDM networks are more static in nature, and you really want to make sure that you're going to switch back, and you really, really want to make sure, right? So whenever the working path gets established, the non-revertive behavior is something that you can define as a local function in Node and say basically, well, we have the working path back up, but we don't want to switch back yet. And we're going to wait until the operator is issuing a command, and then only we do so. And last but not least, that was a fun one. After talking about how we can actually emulate the SONET and OTN behavior, and basically saying, well, we're going to keep our paths persistent, meaning I'm only going to reestablish my old working, and I'm only going to reestablish my old protect. What happens if I have a catastrophic failure and get into a double failure situation? My working is down, my protect is down, but I actually have still some interfaces and links and resources in my network that actually could bring my service up. Why would I unnecessarily bring my service down? Now, all of this is really, again, and some people might, shake their heads. This is all kind of try to please and copy the OTN and SONET behavior. But once you start doing that, you need to go all the way. Otherwise, you're going to get in trouble. But if you do so, with a small little wrinkle here in addition, you could actually just say, OK, the working is down, the protect is down. Let's actually configure my tunnel or my segment routing policy with a third path option. So whenever the first two are down, let's signal an on-demand option that doesn't need to guarantee anything. And if there is something, we can at least bring back the service. And whenever the working and or the protect comes back, we're going to switch to that. And we're going to go back to the normal operation. Latency. I think that's a fun one for me. But actually, it's an easy point to address, right? Routers are no longer CPU-based, right? They are hardware-based. They can forward packets very fast. And the only reason why you would see latency in a packet network these days is if you congest links or congest a certain traffic class, right? Take any router today, they're going to show you, I just take a rough guess here, between 10 and 30 microseconds, depending on the platform and the design of the box. But a low double-digit microsecond number of latency. And by the way, if we think back of what I just said before about how you build an OTN switch these days, the OTN switch is not going to show you lower latency. The actual transfer latency of a big OTN switch is very likely going to be actually higher than of a big MPLS box today. Quickly on one topic, as OTN and SONET networks are heavily relying on, I would say, network management systems to provision those, if you want to propagate failures and state information, you can't use a dynamic routing protocol. So a lot of those things have actually been superimposed into the frame overhead, right? So whenever you have a local failure, some alarm, signal is added into the framer, and the other side might know about that. In our case, if we start using pseudowires and we are actually only having a TDM interface on one end and on the other, we can do exactly the same. We're just using some signaling mechanism. And in our case, if you use LDP, you have a local loss of signal. We're going to translate that into a pseudowire status message. So on the far end, we can then look at that and inject an AIS downstream signal. If you use Ethernet pseudowires, you could do something along the same lines. by basically looking at Pseudowire status and shut down the interface. I know this is, let's say, not a well-defined behavior, and depending on what vendor you look at, you might have an implementation or not. Or you just say, I'm going to go down the standard route and I'm going to use Y7 and 31. That protocol has implemented all of those alarm signals as well. Performance monitoring. That was, honestly, for me, something very interesting, because I have been working on routers for a long time and carry Ethernet, but this piece I completely overlooked. In the TDM world, we can monitor or give an indication of the quality of the signal by using parity. So essentially, on one end, we are looking at the zeros and ones in the frame, and depending on whether you do even or odd parity, you have one or more parity bits, and you set it to 1 or 0, so that overall the number of ones is either even or odd. On the receive side, you look at, and by the way, once you do that, you put that into a frame that later on the receive side you can actually compare. So you can compare two copies, and whenever the number of ones or 0 changes, this is a good indication that something happened to your frame. So you have a bit error, and some block is maybe no longer valid. And by doing this constant frame-based, frame overhead-based monitoring, you can actually detect something like an errored block, an errored second, a severely errored second, and if you have more than 10 severely errored seconds, you're going to call the service to be unavailable. And that's the point that I overlooked over all these years. Actually, many, many years ago, I think nearly a decade ago, ITU and MEF defined something very similar. And I'm not sure if that, for me at least, it was a surprise. So this is a public confession. But Y1563 may not be known to everybody. Now the wrinkle is here also, it's not that widely implemented. But from a definition perspective, if you have now an Ethernet circuit, you cannot do the bit error, the parity bit, right? But what you can do is you can inject loss measurement packets, and you can look at whether you lose some of those packets. And if in a certain interval the frame loss ratio is above a threshold, you declare something like a severely errored Ethernet interval or second. Now, why did I use the word interval? Because when you really want to do that on a per second basis, you can imagine that this is quite a bit of load onto the actual router to do that. And I would say that's also the reason why Y1563 is not widely supported by the various vendors. But it's defined, and you could, if you extend the interval, you could even do an off-box evaluation of these availability parameters. Transparency. I think that was an interesting topic over many years. And I have to say, because Carry Ethernet started by dumping a bunch of enterprise switches into the ground, it was a bit of a painful start, right? In the old days, if you put a switch into your network and all of a sudden a BBDU came in on a port, the switch said, wow, this seems to be a spanning tree packet. I need to deal with it, right? But it was a spanning tree packet from your customer, right? So it took the vendors, including us, I would say a couple of years to figure that one out. Thanks to MEF and various operators, I think we slowly, well, actually, I think it wasn't that slow, but over time we defined what needs to be done, and the implementations got cleared. And now we have clear guidelines what to do with those slow protocol and control plane packets, and we now are able to either block them, tunnel them, or process them depending on what the service is. There's always a but, right? Lately MACsec became very interesting for a lot of people because it gives you a high performance option of encrypting your traffic leaving your box, right? Unfortunately, you're doing a key, per definition, the key exchange is using a well-known MAC address that again, goes into the pool of slow protocols, and today it is very likely going to be the case that a switch that is installed in some provider that may actually drop that packet. The good news, I would say, it's just a question of time the various vendors will actually figure that one out and will start tunneling them based on how you define your pseudowires and services. But also, I can talk for our products, we have provided an option to actually change this MAC address to, for example, a broadcast address, and then you can pass it through as well. So either way, luckily, I think this problem got solved quite soon. Last but not least, simplicity of operation. So this is really more for those of you that need to deal with provisioning DS1s, which I would say is the minority. But think about this, even if you talk about an Ethernet over SONET circuit, and if you, as an ISP, for example, ask somebody to provide you an Ethernet over SONET circuit, they need to go through the TDM network and find time slots. And sometimes they have them, and sometimes they don't have them. Sometimes they need to install new ADMs or do whatever is necessary to accomplish the deal. Now, once you have found all the capacity, you can provision it, and then after that, you basically don't need to deal with it anymore. This is the classic set and forget. But once you're actually done, but until you are done with that, you actually have quite a bit of work to do. By adopting MPLS and pseudowires, you change the paradigm, right? Not only are you using cheaper boxes in between that do the MPLS switching, but you also go directly into a point-to-point end-to-end provisioning model. So you're going to touch an endpoint on one side, and you're going to touch an endpoint on the other side. Your SDN controller provisioning system, or you just sitting on a GUI, say these two endpoints need to be connected to each other, you establish a pseudowire. And then underneath that, you're using some kind of MPLS tunnel of your choice, right? Depending on how you want to run your network, and going to make sure that your traffic is passing from the left to the right side. So in summary, essentially the key takeaways that I would have for you is that this is somewhat an old topic, right? But I think things have changed, right? MPLS routers or switches, whatever you want to call them, are getting bigger and bigger, more cost effective. And really, there is no reason why they cannot provide the same level of service agreements as they do on SONET or OTN infrastructures. And I think as we have seen also in the previous presentation, and probably you guys see in tomorrow's presentation, optics and the speed of MPLS interfaces is increasing, right? 400 gig MPLS interfaces are not far away. They are really around the corner, right? And you will get higher interfaces over time. So really, knowing that the routers are getting bigger and in that way also cheaper, do you really want to continue putting your 100 gig pipes into an OTN switched infrastructure? Or is it maybe time to rethink and consider that MPLS is going to become the new electrical multiplexing/switching layer, right? Whatever you want to call it. And by being MPLS and the native transport for any type of other services, you have the choice to run your network very stringent, and then really you use it as a multiplexing layer, right? You don't overbook, you do have some hard bandwidth guarantees, or you run your network for some services very flexible and potentially oversubscribed, and you can do it on a per LSP or per service basis. With this, I'm at the end of my presentation. Appreciate your time. I actually stopped a little earlier, so if somebody has questions, I'm willing to answer them. And
Joe Hess with Hess Communication. One quick question on this. There's a lot of stuff inside the SONET headers, and you mentioned a tunnel. Where is the tunnel in the system? Is it a separate channel or what? Or is it in the network management system?
You mean the LSP tunnel or?
No, not the LSP tunnel. I've got like the D4 headers. A lot of people put a lot of stuff inside SONET headers. And presumably that's all going to go away and not be part of my LSP tunnel.
Yeah, so that's a very good question. So that depends on, so you're talking about emulating, for example, SONET or DS1s, right? So if you look at PDH, which is DS1 and DS3, right? What predominantly is being used, you take the full frame and just slap on a label and send it over the other side, right?
Oh, so you include the SONET header, the whole full frame in there?
Yeah, so this is the DS1 and the DS3 case, right? Now, if we talk about SONET interfaces being OC3, 12, 48, there we are actually not taking the full frame, because that actually would be very, let's say, bandwidth inefficient, and also it wouldn't allow you to, because normally in an OC12 you have some time slots go here, some time slots go here, right? So what actually is being done, which has been standardized by the standard called CEP, is you look at the path, right? So you get rid of the first two layers, and then you use the SONET path, and you encapsulate that. So you're going to lose your, let's say, LDCC and SDCC kind of stuff, right? Mm-hmm. And you start acting like a real multiplex or a cross-connect.
Thank you.
Steve Ulrich, Arista Networks. I'm wondering if you're suggesting, as a complement to this, that there be a change in the service level objectives for circuit services. A number of the packet forwarding engines on the market from a variety of folks are not capable of actually reaching the kind of line rate requirements associated with that, which would lead to either like suboptimally packing circuit services which are being emulated here, which has a decided negative economic impact. Are you suggesting maybe there's a potential for an alternate tier of circuit delivery from a service level perspective?
Yeah, I think that's pretty much what I'm hinting at, right? I mean, today, I think we're living in a world where people say a circuit is a circuit, a wave is a wave, nobody can take it away from me, right? But if you think about it, that economically this is probably not the most efficient way. I think there's a valid compromise where basically you could say, I trust my operator that he's actually designing the network so that actually I get what I expect, right? And I think this is a fair assumption that has two benefits, right? The operator could start leveraging technology that's better for him, and it's also an option for the customer to say, well, maybe I'm gonna get more capacity for a lower price. Now, from a TDM emulation perspective, I have to say that the actual service level agreements and the performance will be completely identical. Because as you emulate the frames, you even have things like digital buffer management where basically you don't see any difference, assuming that the network is built in a reliable way. But other than that, it will be exactly the same.
Sven Kjærvik with Apple. What about clocking when you go to an MPLS model versus the legacy? Not that I need it, but I'm just curious.
Mm-hmm. Clocking, actually, the problem has been solved. Luckily, many years ago, you now can build an MPLS switch using synchronous Ethernet interfaces. So essentially, you can use the physical media between two routers to transfer a clock. So essentially, on a hop-by-hop basis, you do exactly the same as you would do in the SONET infrastructure. That's one approach. And the second approach, which would apply, for example, in the use case that I showed, where Verizon is using circuit emulation over the access, there you need to rely on things like IEEE 1588 or PTP to derive the clock. And that, together with some Pseudowire-based traffic rate recovery, also gives you good enough clock recovery for that. So there are two options for that. Okay. I think. Thank you very much.